Yeah, exactly. So I'm Simon Bolanos. So I would like to switch gear and discuss a bit more about like experiments using high power laser, in particular to study the initial stage of quasi-parallel collisionless shocks at a high Alfvén Mach number. So the Alfvén Mach number is a ratio between like the flow velocity over like the Alfvén velocity. And here by I mean like we're above like 100, which is relevant to supernova, young supernova remnant. And I will discuss more about like what kind of micro instability we observe in our experiments during this formation stage of the collisionless shocks. So why are we interested by collisionless shocks? So there is a number of observation of shocks in astrophysical context. So here I present two of them at a young supernova remnant and like the closer to us at the magnetopause. So by shock here, I mean basically we have like an interface with the downstream region and the upstream region. The downstream region being like the hotter and denser plasma. And what is interesting is like if you look at the particle mean free path, you will notice that it is like larger than the system itself, typically like as shown here. So basically, collision cannot mediate like the shock as we have in more conventional gas dynamic shocks. So we need like other dissipation to mediate the formation of the shock. And with these shocks, there is also like a number are believed to be, we also observe like an amplification of the magnetic field. The collisionless shocks also are believed to be like a perfect candidate to generate high energetical particle following a power law distribution. So those non-thermal particles are named also the cosmic ray, and to be a good place for energy exchange between electrons, ion, and non-thermal particles. So the first question usually is like, how can this shock can exist? And also, what are the dissipation mechanism like involved in this formation of the shocks? And what is the structure of the shock? Is it similar to the gas dynamic shocks? So now on the left side, I show an image of another supernova remnant, the SN 1006. I depicted like the orientation of the magnetic field. And what is interesting, so if we look at the shock structures and what we call the quasi-perpendicular configurations, so at the outer edge, of course. So quasi-perpendicular means like the flow velocity of the shocks is perpendicular to the external magnetic field here. It's very different to what the structure in the quasi-parallel configuration. So quasi-parallel meaning like the shock velocity is aligned with the external magnetic field here. There is also like other numerical simulations show very similar behavior. So it's like extracted from the study of Damiano Caprioli. What he showed basically is like here are like the density distributions for the parallel configuration, so the figure on the top, and the perpendicular configuration. So like there's more like turbulent feature in this parallel configuration. So what kind of the question like usually people are trying to answer is like how this external magnetic field is important and how does it affect like the shock. In a very similar manner, there is like a number of studies that show that the collisionless shocks are a perfect place to accelerate particles. And they also notice that it is very dependent of like the magnetic field configurations, so orientation of the field and strength. On the left side now I present like a paper of results from a paper of Jolanda. What is showing basically is like it's like an ion accelerated at the bow shocks. So it's like the efficiency of to produce non-thermal particles in terms of the orientation of the field, magnetic field, and the Alfvén Mach number. What you show is like basically we are more, we produce in a more efficient way like particles, non-thermal particles in the in the parallel configuration, so below 45 degrees, and at a higher Alfvén Mach number. Another numerical study using hybrid peak simulations that was done also by Damiano Caprioli show very similar behaviors. Basically, like, so what kind of the people trying to answer is like, what are the mechanisms that produce this non-stable particle? What is the efficiency, depending of like the magnetic field, magnetic configurations? And there's also something very interesting is like, if you generate non-thermal particle, basically you have a new source of free energy, and this free energy will generate a magnetic field that can modify the shock structures. And so you got kind of like this back reactions. And so it is why I was kind of interested to look at in details in the lab those quasi-parallel shocks at the high Alfvén Mach numbers. Hopefully with laser plasma experiment over another capability to study these collisionless shocks in a controlled environment. And in particular, now, I'm going to show you our experiment where we were more interested by this initial phase, so what kind of dissipation mechanisms that occur in the laboratory. So first, I want just to present two experiments that was done in the lab using laser. So the first one was performed at the Omega Laser Facility. I was more interested to see what kind of dissipation mechanism was involved in the unmagnetized shocks. So on the left side, you see like this. So by unmagnetized, meaning that there was any external magnetic field applied. On the left side, so you have the setup of the experiment. The principle is very basic. It's like you have like two foils facing each other. You will irradiate with high power laser each of those foils. It will produce high velocity plasma flows that will interact with each other and interpenetrate rates. Due to the high velocity, basically the interaction is collisionless between the ions. So you need like a micro instability to enable this the interaction between those particles. And so they tried to look at what kind of magnetic field was generated in this interaction to understand what kind of kinetic instability by using a proton radiography technique that I will more describe. But the idea is like it kind of reveals the magnetic distributions in the plasma. So on the right side, I show like this, the images I collected. What you see basically is like these filaments are due to the magnetic filaments that generated during these interactions. And they ascribe like the formation of these filaments due to the iron-Weber instability. So a few words on the iron-Weber instability. So the iron-Weber instability is a streaming instability that develop for counter-streaming plasma. When you got two counter-streaming plasma at high velocity, at the moment you start to have like a current perturbations, you will generate a magnetic loop. This magnetic loop will amplify like the current, and this current will amplify. So you understand like this unstable loop. Another experiment I would just want to discuss briefly, it was performed at the LAPD. So I've been like, the LAPD have been a little bit discussed yesterday. But the idea, so the LAPD generates like, in this experiment, I was interested for the dissipation mechanism in the quasi-parallel shocks at a kind of a low Alfvén Mach number, so around 2. So the LAPD generates the background plasma, the external magnetic field. They just use a laser to generate the second plasma slab. And they measure the magnetic field using the B dots. This is what I show on the right side. And they describe like they measure like the growth of like a magnetic field that they ascribe to the right-hand resonance streaming instability. So the right-hand resonance instability, so it's the streaming instability. So it's triggered when you've got like a ion beams plasma propagating into like a magnetized plasma, a core plasma or a background plasma, with a drift velocity which is aligned with the external magnetic field. So it will generate a electromagnetic wave represented by these red lines. So if you look at like the distribution of the particles in terms of the velocity, here you will have like the core plasma, so the background plasma, which is like more dense than the ion beam. which is represented here, and the unstable mode will be in resonance with the beam plasma. This is why we call like the right-hand resonant instability. But when you start to have like the drift velocity, which is way larger than the Alfvén velocity, so basically like a Alfvén Mach number, which is very larger than 1, you cannot anymore to be you are not anymore in resonance. So you will develop like another like unstable mode, which will be more here. And so this instability is named like the non-resonant instability or the Bay instability. So the idea was like we wanted to, we developed like a first platform for the omega EP to study quasi-parallel collisionless shocks at a high Alfvén Mach number. So on the left side I show the setup of our experiment. So basically we have two facing target to generate the core plasma, so our background plasma, and the beam target, and the second target, what we call like the beam target, where we generate this beam plasma. We apply an external magnetic field using like this system called MyFET, so it's just like a solenoid. And we probe like the magnetic field that developed during this interaction using like the proton radiography. I will give more details after, but first I want to give you more details about like how these two plasma will interact with each other by showing like the rad hydro simulation. So using the flash code. So it will be like the color bar will be the ion density. So typically, as here, we've got like the core target, our two target, core target and beam target. We've got a magnetic field in these directions. So the idea is like first we irradiate the rear surface of the core target here. We create an ablation plasma. The ablation pressure will launch the plasma in these directions. This plasma is pretty slow. Basically, it reaches like the midplane around at 10 nanoseconds after the beginning of the experiment. And what is interesting of this, what we call the core plasma, it's like it's pretty dense. So we have like a small ion inertial length. So like you got some details of this plasma here. 17 nanoseconds after the beginning of the irradiation of the core plasma, we start to irradiate the second target. In this case, we've got like a wave, and we take advantage of the plasma produced at the front surface. So the ablation plasma, which is like more fast, way faster and dilute plasma. So you got like basically like the flow velocity is about like 1500. Experiment, the core and the beam will start to interact with each other. So I want to repeat. So basically, our core target, which is our background target, is dense. This is what we're looking for in order to have like a small ion inertial length. But at the same time, we want the second plasma slab to go fast enough to have like collisionless interactions. And in this case, typically, the mean free path of the ion core and the ion beam is about like 12 centimeters. So compared to the size of the system, which is like 6 millimeters, so we do have like a collisionless interaction between our ion core and ion beam. So as I said earlier, our main diagnostic was the proton radiography imaging. We also feel like other diagnostic in order to benchmark our flash simulation. So the simulation that I just showed you earlier before. So a few words of the proton radiography technique for people who are not very familiar. So the idea is like we generate using a high intensity laser pulse a laminar protons, like as represented here. We collect with what we call the radiochromic film. In this case, typically, like the proton propagating into vacuum. But when like this proton beam propagated into a magnetized plasma, the magnetic field will deflect the protons, and at the plane of the detector, basically we have some accumulation of protons. region where we don't have any protons and some region where the protons are undeflected. And so basically we have like a fluctuation of the fluence of protons, and by looking at this fluctuation, you can try to retrieve the magnetic field distribution inside like the plasma. And so basically on our RCA, so radiochromic films, our detector, the higher is the energy deposit in the film, and it will turn darker. So now I will show you some proton images, which was taken 7 nanoseconds after the interaction between the core and the beam. This is what I call T0 here. So this is 3 different configurations. Let's look at the one on the left. In this configuration, basically we have like the core plasma propagating into the magnetic field. There is no beam plasma. We don't have any like fluctuation of the contrast in this image, meaning like we don't have any like electromagnetic field structures. In the case where we've got the core and the beam plasma interacting without any magnetic field, so the core goes every time left to right and the beam right to left on these images. The only structure we see is like at the middle here, so meaning that we've got like a magnetic field which like accumulates at the interface between the core and the beam. We believe it's due to the advected Biermann battery field, which was created at close to the beam target. But at the moment we start to turn on like the MIFET, so the magnetic field, we have a magnetic field. We have like all this high fluctuation in these images. And we've got like a strong electromagnetic activity compared to the unmagnetized case. So the idea then was to see how this fluctuation evolved in time. So we look like earlier, the one on the left, and later. So 10 nanoseconds later on the one on the right. So the one on the left, that's the one we take like earlier in time. We have like a smooth contrast on these images, meaning we've got like a more like moderate magnetic field compared to the one that I just showed you, where we've got like what we call like caustic structure. So it's like sharp structure with a strong accumulation of protons, which means that we've got like a stronger electromagnetic field. The one later in time, in fact, what is interesting is like a very similar structures, but in addition, like we have like this ribbon which is to be like strengthened, and which is due to some like electric field. But however, like I just want to discuss about like kinetic some kinetic instability that we observe in these images, and we can see some signature by like, some filaments we observe like here earlier in time, which is at the edge of the core plasma, or more inside of the core plasma that we see later in time. We believe the one earlier in time are due to the ion-Weber instability, and the one after are due to the band instability. So I will explain how why we believe such a thing. So to infer like the origin of the instability, we characterize those filaments. To do that, we first so estimate the magnetic distributions using the inversion technique based on these proton images. So from these proton images, we estimate the 2 components of the magnetic field. Then the idea is like to analyze the regions where we've got filaments. Doing by FFT, we observe like a dominant mode around like 100 micrometers. So then this 100 micrometer filament was compared with some model. And on the right side, I compare with the model which is like the quiescent model. So the quiescent model for the ion-Weber instability is like when the ion-Weber instability reaches like the saturation regime, the filament will start to merge, and from this we start to merge, and so the wavelengths will increase. I plotted like this temporal evolution of this filament in blue here, and I compare with our measurement, which is like the green cross here, and we see like match pretty well. So we believe that the filament we see early in time are due to the ion-Weber instability. So we did like the same thing with like the filament we see later in time, the one here inside. So what was it that I reported here? So what is interesting is that those filaments are way larger, about like 400 micrometers, and they doesn't like increase, they don't get bigger in time. Meaning it seems like these filaments are more likely to be in the linear regime of like an instability. Doesn't really match like the quiescent model. And in addition, like the quiescent model underpredict like strongly like the size of our filaments. So we don't believe these filaments are due to the ion-Weber instability. So to understand what was the origin of the slate filaments, we ran some hybrid peak simulations. So here, like kind of the model of our simulations is very simple. We've got two plasma slabs counterpropagating with uniform parameters. We take the parameter relevant for our experiments. Here, the ions are treated kinetically, and the electron has the massless field. So now I'm going to show you like the evolution of the magnetic field for the three components, X, Y, and Z, components of the magnetic field. And so basically you see that there's like a magnetic wave and that get increase in time, getting like a large, the amplitude get larger and larger and after like get saturates. So the first thing was to do an elasticity decomposition of this magnetic field to understand like what kind of what is like the wavelength. So we have like a dominant mode around like 0.3. And then we calculate the dispersion relations from like a model describing the ion beam streaming instability. So to describe the right-hand instability or the non-resonant instability that I discussed earlier. And in this case, we do expect to have like a resonant unstable mode of around like 0.3, which is due to this one is due to like the non-resonant instability or the Bell instability. And it matched pretty well our simulation, since to say that the growth of this wave are due to the non-resonant instability. So then the next step was to compare this filament with our to compare this simulation with our experimental measurements. So now I'm plotting like the temporal evolution of the dominant wavelengths. So the solid like the line are from like the simulations, and like the red cross are like our experimental measurements. So the first thing to note is like in our simulation, like the wave, the size of the wave kind of remained constant, reached before like 7.5, and after increased suddenly because it reached like a saturation, and then after it's like in the non-linear regime. But in the time scale of our experiments, it seems like this instability is like in the linear regime. That makes sense with our measurements. However, we do see that the size of our filament are like underpredict. And that we believe is due to the fact that we don't really include some collisions in our simulations, and also like any gradient profiles of the temperature and density and velocity that you will expect in the blow of plasma. So as I said, at 7.5 we reach like the saturations. So I just want to discuss a little bit about like this turbulent regime. So now I'm plotting like the temporal evolution of the energy. So before 7.5, as I said, we're in the linear regime, meaning we've got just like an increase of like the magnetic energy. When we reach that saturation, it is when like suddenly like the flow are strongly slowed down and heat up. And then we reach like this turbulent regime. Or in our experiments, we just like stay in the linear regime in order to like to drive these quasi-parallel collisionless shocks with the NRI. We need to reach like this turbulent regime. So meaning we need to fuel for longer to drive for longer our beam plasma. And basically it means having like a bigger laser. And so we kind of need to go to like NIF, so the National Ignition Facility, to be able to fully form these collisionless shocks. So now we conclude. So we designed the first experiment for MEGA-EP to investigate collisionless shocks at a high Alfvén Mach number, which are relevant to supernova remnants. We did observe the presence of the iron Weber instability followed by the non-resonant instability. And our kind of like main future, like our ultimate goal will be to go to NIF to see the formation of NRI-driven turbulence concomitantly to the formation of the quasi-parallel shocks at a high Alfvén Mach number and measure what kind of like non-stable particle we have. So on that, I will thank all my collaborators who make this work possible, and I will take some questions.
Thank you very much. Excellent talk, Simon. Time for questions. Can you come and get the phone from me? Much easier. Or use one of those.
Yeah, short question. What's the Bell instability? Is that Tony Bell?
So basically, yes, it's on Tony Bell.
Tony
So the story is it's like the non-resonant instability, but recently, in fact, it kind of have been like put on the side. And recently, like beginning of 2000, Tony Bell wrote a paper saying like it can be very important, this non-resonant instability, to amplify the magnetic field when like the cosmic ray will like will go upstream. And so there is like, and so it become more like.
So it's a branch of this kind of.
So
yeah.
Basically it's the same thing. It has been like just the way he described it was a little bit different. Thanks. With the current.
Other questions? Yes, Ben.
Maybe I dreamed it, but I think you said you saw the resonant streaming instability.
The non-resonant.
Oh, you saw the non-resonant. Okay.
Yes. So basically for the resonance, we need to be at a lower velocity, and we go in our plasma. Laser plasma are go pretty fast, so things will be complicated to have the resonance.
Other questions? Okay, Paul.
This is probably a semantic issue, but I would have thought that an ion resonance would have been left-hand, circularly polarized, unless you're defining a different coordinate system, because ions rotate in a left-handed sense.
So yeah, so like you expect it to be polarized, definitely, yes. What we see, in fact, is like what we measure directly is not like this, the polarized magnetic field, but you will have also like a longitudinal magnetic field will be generated. This is what we see in our simulation. And yeah, you do expect to have to be polarized. After, like the right end or left end will be also dependent of the frame. So since our background plasma is moving, we have to be very careful about like right hand or left end. Yeah.
Any other questions from the audience here? If not, any questions from our virtual audience? Come on, you guys, wake up. Okay. If not, let's thank Simon again for a wonderful talk.
Thank you.